NCBM 0324, Section 1.5, Basics of Factoring Polynomials, Part 5. In the last example we saw, Part 8C, we said that the GCF was 1. We found it to be 1. And then we said for now we cannot factor it, but there may be some factoring to do later on. In fact, because this expression has 4 terms, this is a good candidate for something called factoring by grouping, which again you will learn more about and review later on in the semester. The key for using this factoring by grouping is the fact that there are 4 terms to that expression. It's kind of a little preview of what factoring by grouping is going to start looking at here. But what other methods do we have for graphing in cases where our GCF is 1 or we don't know what else to do from factoring out the GCF? We come to our next method. It's factoring trinomials with a leading coefficient of 1. So now we're looking at trinomials. It's a special case of a polynomial. The name tells us what to expect. The abbreviation tri means we're going to have 3 terms to our expressions. And the leading coefficient simply means that the number in front of my highest power is a 1. Sometimes this coefficient can be other values, and again, we'll see those in the future. But in this case, what can we do if that leading coefficient is a 1 and I have those 3 terms? So we're going to say to factor trinomials of the form ax squared plus bx plus c. So notice I have 1, 2, 3 terms. My leading coefficient, the number in front of the x squared, is a 1. Right? It's an understood 1 in here. When we have this, we want to find 2 integers. And by integers, we mean numbers, whole numbers that are either positive or negative, no fractions, no decimals, integers, whose sum, when I add them up, it equals the middle term, and whose product equals the last term. So all of this really means we're looking for 2 numbers, right? The integers, they could be positives, they could be negative numbers, so that when we add the 2 numbers, when we add them, we get the value of b. And then when we multiply, we get the value of c. We get the last term. So using this method is amounting to finding these 2 numbers. Now a reminder, just like with any method in factoring, sometimes expressions have no factoring available to them. So we can still potentially end up with a prime polynomial, a prime trinomial. We won't be able to find a and b. So we have, again, other ways of finding some of those characteristics that we may need. So let's try this out. Example 9, we want to factor. Factor as much as possible, remember. Part A, we have x squared minus x minus 6. So looking at our setup, we have the right form. We have our trinomial form, a coefficient of 1 in the front, just simply x squared. If I look and compare it, I do want to maybe label out my values for b and my values for c so I know where I'm headed. The b value is the coefficient, the number in front of the x term. So what do I have in front of my x term here? I have a negative, which means that there's a negative 1, right? That subtraction is a negative 1, really. Then my c value over here is negative 6. So I'm looking for then 2 numbers that add to give me negative 1, but when I multiply them, I get negative 6. Multiplied to get negative 6. So going with the multiplication, the negative is calling out here to me. That negative is telling me that whatever 2 numbers I'm picking, I know one of them is going to be positive and the other one's going to be negative, because that's the only way I can multiply and get a negative number. So if I wanted to list out some factors of that 6, I can do 1 and negative 6, or it could be negative 1 and positive 6. But I also have 2 and negative 3, and then negative 2 and positive 3. So again, we're practicing our factor of values of numbers. I think that's it. Those are all my possible factors to get -6 when we multiply. Then we want to check, of these that we have listed, which one adds to be a -1. So when I add 1 plus -6, that ends up giving me a -5. So that's not right. That one won't work. We have -1 plus 6, right? A +6. That'll give me a +5, but I want it to be a -1, so that one doesn't work. 2 plus -3, though, that's going to give me a -1. All right, let's just check the last one just in case. -2 plus 3 gives me a +1. That's the wrong sign. So it looks to be that our numbers are the 2 and the -3. So those are my integers that my method is calling for. Once I have those integers, though, my factorization is really quick. So our x squared minus x minus 6 is going to equal to the following factorization. We'll use parentheses, 2 sets of parentheses, to indicate our factors. Now the only way to get x squared with multiplication is going to be to multiply x times x. That's how we'll get that x squared. Then these numbers are the rest of my factors that I'm looking for. So I'm going to have a +2 and a -3. So you can see already how different this factorization looks in terms of an answer. We have multiple sets of parentheses, but the key thing here, they're still being multiplied. We're still breaking apart those 3 pieces into a multiplication of 2 smaller pieces, right? These are called binomials because there's 2 terms to them. So we have a trinomial into 2 binomials. And the same way we checked our previous answers, we can check here. And this process of checking is sometimes referred to as FOIL, when I do a binomial times a binomial, which we practiced in that function section in our previous videos. So we would have to multiply first term, so that's how we get the x squared. Outside terms, x times -3, that's -3x. Inside, 2 times x is plus 2x. And then 2 times -3, that's the last term. That gives me the -6. So you can see where these rules kind of come from. If I need the middle term to add to be that b value, right? We need to match it up there. I have to make sure that whatever I multiply to get the last term, that addition will result in that b value. So that's why we got to check, do they multiply to give me the last term? And the numbers, do they add to get me that middle term, right? That 1, that b. So checking, it's really, really useful, right? It's not too complicated. It's a nice practice of the distributive property, and it just makes sure that we understand where everything's coming from and how everything is related to each other.